We generally expect the small, distant moons of the outer solar system to be quiet worlds, spheres of frozen ice and rock, heavily scarred by billions of years of impact craters. That assumption held until 1979, when the Voyager 1 spacecraft arrived at Jupiter and pointed its cameras at a moon named Io. Instead of frozen rock, Voyager revealed a landscape painted in bright yellows, oranges, reds, and blacks. Crucially, the ancient craters we expected to find were missing entirely. Planetary science shifted in an instant with the discovery of active, towering plumes shooting volcanic material hundreds of kilometers into the vacuum of space. Because fresh layers of volcanic material bury older rock almost as soon as it forms, Io effectively erases its own history, making it the most geologically active world ever observed. Volcanism on Earth is primarily a product of residual heat from the planet's formation and the internal decay of radioactive elements deep underground. But Io is only about the size of our moon. It is far too small to have retained this internal planetary heat for 4 billion years. Without the internal radioactive fuel that keeps Earth's mantle churning, an unseen force must be generating the massive heat required for these endless eruptions. Finding that source requires looking away from the colorful surface and into the dark space above. Jupiter contains more than 300 times the mass of Earth. This massive physical scale gives Jupiter an overpowering gravitational grip, keeping the small moon Io on an incredibly tight leash. Io is locked into an orbital resonance with 2 other moons, Europa and Ganymede. As they align, their gravity yanks Io from different directions. These tugs force Io into an elliptical orbit, where the gravitational forces constantly change. This specific arrangement of massive bodies traps the moon in an inescapable gravitational tug-of-war. That tug-of-war powers a mechanical process called tidal heating. Think of a rubber ball being repeatedly squeezed and stretched. That constant motion creates internal friction, which quickly generates heat you can feel. Io experiences this same physics on a planetary scale. Its solid rock is deformed, bulging and flexing under pressure as its orbit shifts. This friction melts the deep rock, creating massive subsurface magma pockets that push toward the crust. This sequence converts gravitational energy into the thermal heat powering the moon's internal engine. When that subsurface magma finds a pathway through the crust, the resulting volcanism reshapes the moon. At Loki Patera, a massive lava depression spanning 200 kilometers, enormous amounts of heat escape from the moon's interior through cooling lava. Other regions, like Pele, exhibit chemical extremes, with sulfur-rich eruptions painting the landscape in giant dark rings. The sheer volume of these volcanic deposits creates enough crustal pressure to fracture the surface, forcing jagged ridges upward to form mountains several kilometers high. These towering mountains, sprawling lava lakes, and violent plumes act as the literal exhaust vents for the gravity machine deep below. Io's violent surface is a system working in a predictable, rhythmic sequence. Jupiter pulls, the neighboring moons disrupt the orbit, the interior flexes, and the volcanoes erupt to release the resulting heat. While Earth is powered by its own internal heat reserves, Io's geology is driven entirely by the gravity of the worlds around it. It functions as a massive, never-ending planetary machine. Because of this constant activity, Io provides a priceless laboratory for planetary scientists. It reveals the absolute extremes of how planets lose heat and demonstrates how gravity alone can reshape the surface of a world. This moon proves a world doesn't need to be massive, have an atmosphere, or orbit close to a star to remain violently active. In a solar system often viewed as a collection of static, frozen objects, worlds like Io burn relentlessly to reveal the fundamental physical rules governing the cosmos.